I received my PhD actually from ASU in 2015 in civil, environmental, and sustainable engineering. And then I went on to get my postdoc at the EPA at one of their research offices located in Cincinnati. My work both as a, I'm sorry, I'm just getting some of the stuff squared away right here. My work as a, both as graduate work at ASU as well as my postdoc work at the EPA pretty much predominantly focused on different life cycle assessment research. So development of LCA methodology, development of life cycle assessment inventory, a range of different applied life cycle assessment, actual applied LCAs themselves. And I did that through both my graduate research as well as my postdoc, and then a little bit of work on the side as a consultant for my own LLC. So I've done applied LCAs and what's called environmental product declarations for the pharmaceutical industry, the lighting industry, water purification, bleach. I've done life cycle assessments on kitty litter, actual industrial energy scale systems. So the good thing about LCAs, and I'll be getting into all of that, you know, as I get into my presentation, is that they can literally allow you to study any product, service, or system and understand what its environmental and human health attributes would be throughout its entire life cycle, or, you know, cradle to grave supply chain, or hopefully even cradle to cradle supply chain. And I'll get into that as well. But I, you know, like Ann said, I have worked either as directly as a colleague with, you know, some of you, both at my positions at the city of Mesa as well as Maricopa County. But yes, I did chair this this group for about 2.5 years, from 2019 to 2022, just about 6 months ago, and it was an absolute blast, like, you know, chairing this group. And I'm just, you know, really excited to be back here speaking with you all again today. That being said, I, you know, if you don't know me, or if you haven't, you know, seen me as chair for this group 6 months ago, or worked with me directly as a colleague, my name is Scott Unger, and I am a sustainability engineer for the Pacific Northwest National Laboratory. I work on a number of different projects at PNNL that can be anything, you know, related to water infrastructure, both its resilience and sustainability. There's also a lot of work with respect to lighting, which is what I'm going to be talking about. A lot of work with respect to hydrogen infrastructure. There's also some work I'm doing with respect to nuclear capabilities, because PNNL has its hand heavy in a lot of different nuclear related research. But the topic that I'll be focusing on today is, you know, the title of this presentation, which is the development of a LCA template and EPD guidance for the lighting industry. So as you all know, lighting is a major component of the projects, you know, that you all and, you know, that I'm working on as well. The purpose of this project is to further the sustainability for both lighting products and the lighting industry as a whole. Here at Pacific Northwest National Lab, I'm just going to give you a kind of the text or the verbiage that they provide for us to give at just about all of these presentations. But we are a national lab with a Pacific Northwest roots and a global reach. Whether our research are researching the complexities of Earth's climate, helping modernize the U.S. electric power grid, or safeguarding ports around the world from nuclear smuggling, we accept great challenges for one purpose: to create a world that is safer, cleaner, more prosperous, and more secure. So PNNL is working with leading U.S. manufacturers and international stakeholders to develop and refine a standard life cycle assessment, or LCA methodology, for the lighting industry. And a complete LCA is an essential first step to both understanding and quantifying embodied carbon and other environmental impacts of lighting, mechanical, and a range of different electrical products. But it's also an essential step to identifying opportunities to reduce embodied carbon and a range of other environmental impacts that might be pertinent to that product. We are working with several different entities, that being FineLight, Acuity, the Green Light Alliance, and a team of in-house LCA experts. FineLight right here is a relatively small lighting manufacturer, at least when compared to Acuity, which is the North American market leader and one of the world's leading providers of lighting products. And the Green Light Alliance, their aim is to help the lighting sector understand their role in both adopting and promoting sustainability, as well as circular economy, as well as adopting industry standards that are universally recognized, trusted, and sought. So first, I'm going to cover exactly what life cycle assessments are and how they can benefit the lighting industry. LCAs are research methods used to gain an understanding into the full life cycle impact of a material, product, or project. A common misconception is that an LCC is a life cycle costing assessment. While similar in nature, life cycle costing assessments address only economic impact of a product or process's life cycle, whereas an LCA addresses a range of environmental and human health impacts. And so an LCA addresses the need to evaluate complex relationships between products, as well as their effects on the environment throughout their entire life cycle by considering all the inputs and outputs of that particular system. In industry, an LCA may be based on a set of data gathering standards, which is called product category rules, which is what ultimately we're looking to help inform as we further this research down the line. But there are hundreds of different PCRs for various different products, that being product category rules for different types of construction products or pharmaceutical products. These PCRs are essentially the recipe or the methodology that speaks to how do you perform an LCA such that when you compare one LCA of, let's say, a steel beam used in construction, when a competitor is doing the same or doing their own LCA on a similar product, how can they essentially follow the same rubrics or recipes such that they have comparable analyses and that people selecting different products are able to make informed decisions about what are the overall environmental impacts of those products throughout their entire life. So the first step of an LCA is the goal and scope definition, which has several different defined variables. The first is the system boundary, which delimits which processes should be included in the analysis of a product system. The second is a functional unit, which defines precisely what is being studied, quantifies the service delivered by the system, and provides a reference to which the inputs and outputs can be related, as well as providing a basis for comparing and analyzing alternative goods and services. So what that all means is that the functional unit enables different systems to be treated as functionally equivalent. Another way to look at it would be to ask the following questions about what is being studied. What is being studied? How much of it is being studied? For how long and how many times? Where is the study being performed? And how well is the function of the product or service that you're looking at? The second step, and all of these steps are actually clearly defined within ISO standard 1440, all the way ranging up to ISO 1444. And the second, which is defined in 1441, is the the life cycle inventory analysis, which involves creating an inventory of flows from and to nature for a particular product system. It's essentially the process of quantifying raw material and energy requirements, as well as air emissions, land emissions, water emissions, and other releases over the life cycle of a product or process. The third step is life cycle impact assessment. This phase of LCA is aimed at evaluating the potential environmental and human health impacts resulting from the elementary flows determined in the second step, that being the LCI. And the fourth and not necessarily final step, because it's performed iteratively throughout the LCA, is the life cycle interpretation, which is a systematic technique to evaluate and summarize information from the results of the life cycle inventory and life cycle impact assessment. The outcome of this interpretation phase is essentially a set of conclusions and recommendations for the study, which can include identification of environmental hotspots, as well as potential comparative environmental analysis. The functional unit for this study, which is the luminaire providing, or the functional unit for this study was a luminaire providing a outgoing luminous flux of normalized to 1,000 lumens when used at full output during a normalized usage of 35,000 hours. So explained in this equation, this E is the environmental impact of the reference product, And then we have the outgoing luminous flux of the reference product normalized to 1,000, multiplied by the reference product lifetime in terms of hours. And then this is the lifetime of the product where it, again, is normalized against 35,000. And what this essentially allows us to do is that we have defined a certain lighting output and we're going to define a certain lighting output to normalize it against 1,000 lumens. Is defining also the normalization of the lifetime of that lighting output. So that being 35,000 hours. So we're basically saying how powerful is the light and how long will that light run? And that's what the functional unit is, or what the overall function of our system. So there are several different types of LCA analysis that I alluded to in the beginning. There is cradle to grate, which is right here, or cradle to gate, which is an assessment of the product life cycle from resource extraction to the actual factory gate. So this is before it ever arrives to the consumer. This is essentially the creation of a product, and it is literally at the factory gate ready to be shipped to the consumer. So the use phase as well as the disposal phase, use being right here, as well as disposal, as well as distribution, are omitted from a cradle to gate analysis. Excuse me, I can get some water real quick. A gate-to-gate analysis is a partial LCA, which you can see is this little sliver right here, looking at only one of a value-added process throughout the entire production chain. So if you were to essentially stitch together a bunch of gate-to-gate modules, you effectively could create yourself any level of LCA analysis. There is also well-to-wheel, which is a specific LCA used for transport fuels and vehicles. The first stage of this analysis incorporates the feedstock or fuel production, as well as processing, fuel delivery, and energy transmission, which is all called the upstream stage, while the stage that deals with vehicle operation itself is called the downstream stage. The well-to-wheel analysis is commonly used to assess total energy consumption or the energy conversion efficiency and emission impact of different motor vehicles, namely, or what's most common is their carbon footprint. Then cradle to grave is which goes all the way around this wheel right here, is the full life cycle assessment from resource extraction, i.e. the cradle, to use phase and disposal phase, which is the grave. This is the context for our lighting analysis, or this project, which captures raw material extraction, manufacturing, use, disposal, and all of the transport processes between raw material extraction, manufacturing, use, and disposal. And then lastly, there is cradle to cradle, or cradle to cradle, which is where the end of life disposal step for the process is a recycling process. So the last step is not it being incinerated or going to a landfill or some end of life process where it will not be reused. In this case, a good example would be like asphalt pavement being used from discarded asphalt pavement, or new glass bottles being produced from collected glass bottles, such that you don't need raw virgin glass materials or asphalt materials to create a usable product. So this project investigated the potential for standardized data collection, for a standardized data collection template and analysis methodology to establish product, what's called life cycle inventories using public data and other inputs. A standardized methodology and publicly available data inventories would enable easier and more streamlined LCAs to be conducted by lighting manufacturers, while helping to establish, like I alluded to earlier, a level playing field to support competitive sustainable development in the market, such that whether or not you're a small manufacturer or whether or not you're a large manufacturer, you have the ability to effectively perform an LCA on the different types of products that you're manufacturing. And further, you can use those LCAs to procure EPDs that can be used in the market to help further inform specifiers, consumers, any retailers, or anybody for that matter, to help inform about the overall sustainability of your product. The aim of this work, specifically, is to go into depth in the data collection process with one small and one large US manufacturer to really understand, or at least better understand, the roadblocks, gaps, opportunities associated with the LCA EPD process. So we want to know what is making it most difficult for these large and small manufacturers to perform these LCAs and EPDs, and how can we help alleviate or mitigate those concerns. We also want to help ensure a common PCR will be adopted and accepted by stakeholders, including industry regulatory bodies, such as California BiClean, so that again that they are all using the same methodology for performing an LCA, such that there is a harmonization of comparability between the different types of lighting products from different manufacturers. And lastly, identify areas where generic databases and generic information could be applied to help streamline this process, as well as to increase, again, harmonization and comparability among fixtures. So the first phase outcomes of this project, and we're in the first phase of this project, we're actually just finishing up our fiscal year within the next month, and then that officially concludes the first phase, and we'll be on to the second phase. But the first phase outcome is to provide guidance to the lighting industry to improve comparability and accuracy of PCRs, LCAs, and LCIs, as well as provide suggestions and approaches for next steps for LCA adoption in lighting in the US. So as we mentioned, we are working with several entities to achieve these goals. We have FineLight, who is actually providing luminaire data for use in the analysis. They're also helping advise us on template design and data collection. There is also Acuity, and they have a similar role where they're advising on template design and data collection, as well as providing support for collecting LC data needed for the analysis. And lastly, there is the Greenlight Alliance team, who is similarly helping advise us on template design and data collection. So as described earlier, you have the system boundary, which is associated with the life cycle assessment, and this is the system boundary that we have developed for this project. In this case, we have materials, production, and transportation, which is this blue box right here. The three primary materials are the actual power supplies of the luminaire, the light source, as well as structural components. These are either sent directly to production and packaging, or they undergo pre-processing prior to production and packaging. The fixture is then transported, and then it's installed and used. And a little bit of a spoiler alert here is that the LCA analysis, at least our preliminary results, have indicated that this phase right here, the use phase of the light, is the driver of, frankly, all environmental impact categories, but I'll get into that on, I believe it's the final slide of this presentation. And the fixture, or hopefully different parts of the fixture, are either sent to a landfill, or they're recycled and reintegrated back into the supply chain. It could be, back into the supply chain, or it could be reintegrated in a completely different product supply chain, depending on what the nature of, that different waste is and how usable it might be. So on the previous slide, I spoke of the three primary materials, which are the power supplies, the light source, and the structural components. And real quick, you'll see letters preceding the stages on the top left of the screen. If you can see right here, it says A1. These letters are associated with the specific stages that are defined within the PCR. So A1 just happens to be the material stage, and you'll see that there's an A2, an A3, A4, and then we have Bs and Cs and Ds and all that good stuff. But you'll see as we move on that there are the different life cycle stages are identified with these different letters. The light source, or the first of the different three primary materials, is the lamp or integrated lighting components, which can be the actual LED, the CFL, or the HID. The structural components include components that provide light distribution, positioning, and protection. And this is where things can get really complicated. And I'm going to essentially just name all of the different types of materials that are included in structural components, and that the LCA analysis that we have developed is able to account for every single one of these with increasing and sometimes decreasing levels of fidelity. But in terms of structural components, there is anything from a range of different metals that can be steel, aluminum, copper, bronze, brass. And then there's the actual finishing themselves, the coatings, the paints. There's zinc, there's powder, there's electrostatic tinplating, enameling, there's chrome. And then there's also ceramics. There's also all of the plastics associated with it, which can be polycarbonates, acrylics, ABS, nylon, or HDPE. There is glass. There is the actual packaging associated with the luminaire or the fixture, which includes the pallets, the corrugated board, different types of thin films or polypropylene straps. And then there's all of the ancillary stuff, which includes degreasers, surfactants, detergents, acid cleaners, different types of oils. We have connectors, interconnects, harness, the driver itself. As you know, the driver, which is the part sometimes most likely to fail within the actual fixture itself. But all of these different things that I named right here, they exist within our database of information. And unfortunately, the really good databases that we're utilizing, they're all proprietary and they're for pay, but they're really fantastic databases. That the one that we're using, it's called EcoInvent. It was developed originally by the Swiss government, but then was dealt into private industry and has been supported by not just industry for the past couple of decades, but a range of different government or NGO stakeholders that have helped to build out that database such that we can capture all of these different components when performing a life cycle assessment. But again, all of these different things are included, and the way that they're inventoried is through this slide right here, and this is a screenshot of the actual template itself. Or at least the tabs, or at least one of the tabs on the template. It's kind of small, but you can see like on these different lines right here, it says plate, housing, diffuser, LED, driver. This is where the different materials are listed out. And hopefully, it is as granular as possible, such that hopefully you can get to the original bill of materials, but that really just depends on, the manufacturer and the particular product being studied. But there's a bunch of information that is entered here that is essentially directly inputted into the LCA model as needed. These variables include the kilogram of the material, the number or amount of pieces within that material, and then those two are calculated for total weight and weight percentage in those gray columns. Then the different type of component type is entered, and this is where a number of dropdowns become available to the user based on their input in the following columns. And I'll explain that dynamic on this next slide right here. So based on the user selection of either light source, structural, or power supply, these are the dropdowns that can become available. So you see light source, power supply, structural. And if they select light source, you get light emitting diode, CFL, or HID. And then same thing with power supply, you get these selections, so on and so forth. And basically what you're trying to do is get to the point where ultimately you get to what's called a UUID pointer. And so let's say you select light source and you select a light emitting diode, which is right here. And that directs you to the actual UUID pointer. And this is important for two reasons, the UUID pointer. The first being because it is when you no longer have to do any more dropdowns, yay. And the second is that it is when you've arrived at a point where the LCI data that we are using is representative of what that user selection is. So, for example, we have very good information on what are the inputs and outputs associated with a light emitting diode, but when somebody selects something like an HID lamp, well, there's a lot of different types of HID lamps. There's a metal halide, there's high pressure sodium, so on and so forth. And further is that if you're going to select, different types of metals, like steel, aluminum, copper, well, what about the finishing of the metal? What type of metal is it? How is it formed? So all of these are questions that are entered by the user in the model and then ultimately included in the actual LCA. So this tab represents the actual manufacturing of all those components into the actual end usable fixture or luminaire. In many instances, you can see right here, it's kind of small again, I apologize, but there are, in fact, nearly in all instances, there's electricity input. In many instances, there's natural gas input, but then you might also need other products to also integrate within the luminaire or fixture itself to make it that end usable product. This is also where any waste are inputted, as well as atmospheric emissions and emissions to water. So this tab, the installation of the fixture, this is still under development, but this the installation of the fixture itself involves several different processes. The primary one of those is the actual transport from the facility gate to the user site. And sometimes this involves, say you have a fixture coming from China, it will likely involve at least 3 different legs where there is a truck transport step from the facility manufacturing gate to the port. And then there is a transport step of oceanic or ship or barge transport from one port to a US port. And then there is the trucking of the luminaire or fixture itself from a US port to the user site. But then there is a range of other inputs that can also be included within installation of the fixture. There are the fixing elements to the frame if they're not actually supplied with the product. There's any assembly elements, as well as any electricity inputs that might be associated with installing the fixture as well. And so this tab represents operational energy use, which, as I indicated earlier, is the primary driver, at least of our preliminary results. And again, I say that they're preliminary. So we're working out all the kinks of our model, and there's still stuff to iron out. But it's very likely that the actual operational energy use of the fixture is going to remain the driver of perhaps all of the environmental impact categories. Like we said, regarding the operational use, that being when the actual fixture is installed and providing light throughout its entire lifetime. These are normalized to a common functional unit, which is normalized to both 1,000 lumens over 35,000 hours. But there are also several inputs that allow for calculation of operational energy use, including voltage, current, and power losses. And if these are the driving variables of operational energy use, that being total power use, power conversion factor, power draw, all of these factors up here, we know that to most effectively drive down the environmental impact of a fixture or luminaire, that these are, at least for now, the variables that we're wanting to focus on. And the good thing is that, as you all know, because you all commonly are doing lighting projects, the wattage on these fixtures are constantly going down on a yearly basis. The LED tubes, I remember when I started, they were at like 18 or 19 watts, and now I'm pretty certain that they're below 10. So while the operational energy use is still the major driver of environmental impacts, there will be, as we continue to drive down the actual wattage of it, there's going to be a time when there are other components of the life cycle phases of a luminaire or fixture are going to become increasingly more critical towards understanding how we can reduce their impacts as well. But then there's what's called the C and D modules. The C module is the transport to disposal, as well as the actual disposal phases. So we're, at least within our project, we're assuming that 100% of the product is either going to be disposed of or recycled. And that's what we're really trying to work out right now, is what are going to be the assumptions associated with this end of life phase? Will we have any sorting and processing? Will there be any refurbishment, reuse? Exactly how will these components be modeled? We're pretty certain at this point that we're going to be using recycling data from the 2020 U&U report, which is a global e-waste monitor that publishes recycling rates by region. But again, this is a topic that we're going to be taking a much harder look at once we commence phase 2 at the turn of the fiscal year. So ultimately, what the goal we're trying to achieve, and these are all of the different tabs within the template itself, And you can see I've covered just about all of these. I know I left some of them out, but that's because they are still under major development at this point. But the goal that we're trying to achieve is that the template entries as defined by the user are going to generate a list of values for OpenLCA, which is a platform. It's an open source platform that allows for LCA modeling. But when the user inputs their template entries, that there's going to be a automated list of UUID values that can be inputted into EcoInvent. And further, that they would be able to be inputted via a SQL command generated from the actual template and then implemented into the OpenLCA model, that modeling software. And potential future work is going to include being able to export those results into an actual EPD report form, as well as generate the PCR, also known as the product category rule, for utilizing template and EPD reporting tools. And so I believe this is my final slide, which again is our very most preliminary results. I expect they'll change, but hopefully not. We'll see how much they change, but these are preliminary results. You can see the operational use, that being the orange bar right here, is the driver of all impact categories, with the exception of metals right here. And there's mixed results for the different three components of the fixture. In some cases, the structural component is the driver of a category, and the others, the light source or the power, is the driver of impact categories. It really just depends on what the impact category here is, and that's really the beauty of LCA, is that there are a suite of different environmental and human health impact categories. You can see a photochemical oxidation potential, acidification, eutrophication, global warming potential, which is the hot button one that everybody is interested in these days. But then there's also human health categories such as cancerous effects as well as non-cancerous effects. But I admittedly don't have a full understanding of these results just yet, because we kind of just crunched the numbers real quickly to see what we have. But at this point, I can discuss them as eloquently as I possibly can, and I think that's a good segue into some questions if anybody has it.
Great, thank you so much.
Yeah, thank you.
Thank you so much, Scott. So I will go ahead and open it up for questions. And we didn't get any in the chat, but if people have questions, they can easily unmute themselves to ask you directly. And one thing I have a question of is all your data set, or are you, in certain cases, are you making assumptions with some of the data that's taken into consideration?
Yeah, there's definitely a range of assumptions. So, I think a good example of that would be something like the distribution to the user. The manufacturers, they have a very good understanding of where the products are going, but it's not exact. It's not like they have, in some cases, for small manufacturers, they know exactly what, types of products are going where, but to actually be able to perform the LCA, we need to not just know what products are going where, but exactly what weight of the products are going to those destinations. And that's just information that, a lot of times the manufacturers don't possess. So we'll make assumptions about, what is the distance associated with their shipping, so we'll ask questions about, who are your, where is most of your clients? Are they located in North America? Are they located in other regions? Hopefully we can get as granular as possible, because if we could have data that said, yes, we are shipping, this much product to this location with these weights and these distances, then that's it, we wouldn't have to apply any assumptions. But in many cases, that's just data that the manufacturers don't possess. So that would be one instance, yeah, there is certainly assumptions associated with the model, but hopefully we can obtain and use as much primary data as possible.
Great. And you had mentioned that this is a model that will be available online and publicly accessible. So is there a time frame associated with it specifically when manufacturers or others can utilize it, or is this kind of in the planning stages?
Planning stages. So the PCR needs to get adopted by what's called a program operator or like an EPD program operator. UL is a very well-known EPD program operator as well as EPD International. The PCRs a lot of times get developed by those operators, and it's a very difficult, time-consuming, resource-consuming process, and that's the benefit of this work to the industry as a whole, is that the operators don't have to necessarily do all that legwork to develop this template and develop the PCR. But the next phase of the project, that being the phase 2, again at the turn of the fiscal year, is to begin engaging with the program operators to say, yes, we now have this PCR, which will be developed sometime within the next, I would say, 6 months. And what are the improvements, additions, adjustments that can be done to it, such that you would feel comfortable adopting this as your PCR, as well as the corresponding template to go with the PCR. In terms of a specific timeline, we're at least a year out from the PCR and the template, I would say, being publicly, well, I would say give or take about a year from the template and the PCR being publicly available. So you all got a free sneak peek.
Thank you. Any questions for Scott? No? Did everything make sense? I was going to say how it, oh, it looks like Angelica has one in the chat. It says you mentioned one of the outputs of the LCA is the HPD. Well, will it be part of your final interpretation?
Yeah, so the HDPE, the high density polyethylene, that is a component. I'm not sure exactly which component, whether or not it's the power supply. I don't think it would be part of the light source, or it's likely part of the structural components. But so yeah, those are actually included as an input into the system, as likely, again, one of the structural components. And the actual results, as you can see right here, I think you can still see my screen, is that the results are broken down in terms of structural, light source, and power. But again, these being preliminary results, we haven't had a chance to further break those down into even more disaggregated subcategories, or the actual components that make up those 3 different categories. So for example, if HDPE is a driver of these environmental impact categories, you're going to see it show up as a color within this bar right here. At this point, though, I can't speak exactly what are the impacts of the HDPE. Usually, it's driven by the weight of the actual component, but it really just depends. Like, for example, with metals, an equal weight of aluminum versus an equal weight of stainless steel are going to have considerably different environmental impacts because of the production process associated with them. But if HDPE is used in a considerable amount, or has a significant weight associated with it within the structural components, I would anticipate it's going to show up in these results right here.
Thank you. Angelica, did that answer your question? She says, let's see, I want to make sure I have the chat. She said, no, I meant the health product declaration. Sorry.
I admittedly, I'm not too familiar with the health product declarations. I know that we've spoken briefly, with manufacturers on how they can use corresponding information, or potentially overlapping information from the health product declaration in the environmental product declaration. And I think correct me if I'm wrong here, the bill of materials, is something that's included in the health product declaration, right? Yeah, so that would be something that's incredibly useful with respect to an LCA analysis. And the question with respect to the health product declaration, are you asking, are we using HDPE's health product declaration in any way within our LCA? Okay. No, actually. And the short answer to that is because the database that we're using, that being EcoInvent, has already populated HDPE as different flows within the database itself. So part of the difficulty with using LCA is that they need to be like harmonized flows so that you're using the same databases. Because if you're using one source versus another one, one might be inflated or underinflated. But there's a range of different HDPE production processes within the EcoInvent database. And that's actually, plastics are one of the really well-populated processes within the database, where it's like, if I want to select, HDPE produced in, China or the United States or in Europe or Brazil, it basically has like all the electricity grids associated with those different regions, as well as any differences between the regions in their manufacturing processes. So no, we're not using the health declaration statements, but we have a pretty reliable source for the data with respect to HDPE.
Thank you.
Yeah,
thanks for the question, Angelica. All right, any other questions for Scott? So my last question is, once this model is up and running, how do you anticipate it being distributed? Like, how is it going to be promoted? Is it going to be for obviously manufacturers, but also for the private sector, public sector? How do you see it being pushed out through various channels?
Yeah, I see 3 different entities that are going to be spearheading that campaign. There's obviously us, PNNL. We have a team that is going to set up a web page and lead you to Google results. If you Google lighting template within the LCA industry, I know that we have search engine optimization experts that will enable that. But then there's also Green Light Alliance, who we're working with directly, and they're going to help to plug this into the actual lighting industry itself. And then there is the program operator. So whether, I'm not exactly sure who that's going to be, but they're obviously going to promote it within their different marketing, so that when I used to be doing EPDs as of 6 months ago, but I don't do them anymore. I'm now developing guidance for them. But if I wanted to develop a EPD for a certain product, the program operator will pick up this PCR, and if I search within their database lighting products, this one's going to show up. So it kind of it helps to become as an available search item for any relevant LCA researchers.
Thank you. Great. All right. Scott, thank you so much for this introduction into what you've been working on for lighting. Specifically, it's very complex, I must admit. So you did a great job explaining it. I think for those of us that aren't, involved in the nuts and bolts of the modeling and the data. So thank you so much for doing that. I really appreciate it.
Yeah, absolutely. I really appreciate everybody coming to listen to me for a little bit. It's been nice seeing everybody at least electronically for a little bit, and yeah, wish you all the best, and hopefully we can talk again soon.
Yeah, you're always welcome to our meetings.
Most definitely. All right, thanks, Anne.
All right, thank you.